This lecture discusses the critical value approach to hypothesis testing. There are two different approaches to hypothesis testing. The first one is called the critical value approach. In order to draw a conclusion about a hypothesis testing problem, we find a cutoff point based on the significance level. Whether rejecting H0 or not depends on whether your statistic is larger than or smaller than this cutoff point. The next one is the p-value approach. It calculates a probability to evaluate how likely observation of the value obtained for the test statistic would be if the null hypothesis is true. Both approaches are important and commonly used. You need to understand both. In this section, we only discuss the critical value approach. Let's look at one example. Jack tells Jane that his average drive distance of a golf ball is 275 yards. Jane does not believe it. It is a hypothesis testing problem. The null hypothesis is mu equals 275 yards, which is Jack's claim. The alternative hypothesis is mu less than 275 yards, which is Jane's suspicion. Notice that for the null hypothesis, it usually contains words such as equal. Hence, we put mu equals 275 as the null hypothesis. Because Jane does not believe Jack's claim, Jack hits 25 drives. The results in yards are shown in the slide. In this table, in this problem, the sample size n equals 25, and the sample mean is 264.4 yards. The sample mean is smaller than 275 yards. There are several possible reasons that can lead to the fact that the sample mean is smaller than 275 yards. First, the population mean is indeed smaller than 275 yards. Of course, Jack will not agree on it. Second, it is due to random chance. Although the sample mean is less than 275 yards, there are indeed some distances larger than 275 yards. If Jack hits another 25 drives, it is possible that the sample mean is larger than 275 yards. If we can rule out the possibility of the second scenario, that is, if the small sample mean is not due to random chance, we will tend to reject H0 and claim that Jack's mean drive distance of a golf ball is smaller than 275 yards. The logic of the hypothesis test is that if H0 is true, the sample mean distance x bar should approximately equal to 275 yards. If the sample mean driving distance is too small, is too much smaller than 275 yards, we would be inclined to reject H0 in favor of alternative hypothesis. Here, we need to find a cutoff point for too much smaller. Assume that Jack's driving distances are normally distributed and that the population standard deviation of all such driving distance is 20 yards. If H0 is true, x bar is normal with mean 275 and standard deviation 4. This claim follows from the property of the sampling distribution of sample means. Notice that mean of the sample mean equals the population mean. When H0 is true, the population mean is assumed to be 275. The standard deviation of the sample mean is the population standard deviation divided by square root n. Here, 20 divided by square root 25 equals 4. As we have discussed, a small value of x bar supports an alternative hypothesis, and a large value of x bar supports a non-hypothesis. We can calculate the z-score for x bar, which is x bar minus 275 and divided by 4. Recall that this score indicates the relative standing of a value. We will select a cutoff point in terms of z-scores. In this case, we will reject h0 if the z-score is too small. Recall that for a hypothesis testing problem, we will set the significance level alpha, which is the probability of type 1 error. A type 1 error occurs if we reject h0 when the null hypothesis is true. Now, we have assumed that the null hypothesis is true. Let us select a cutoff point corresponding to 0.05 probability of type 1 error. We will reject h0 if z is too small. The cutoff point will be selected such that the area to the left of this cutoff point is 0.05. According to the standard normal table, this value is exactly negative 1.645. This cutoff point divided the range of z-scores into two parts. If a z-score falls on the left of this cutoff point, we will reject h0. If a z-score falls on the right of this cutoff point, we do not reject h0. For the data we collected, x bar equals 264.4. Calculate the z-score. It is negative 2.65. This z-score falls on the left of the cutoff point, negative 1.645. Therefore, we reject h0 and claim that at 5% significance level, the data provide sufficient evidence to conclude that Jack's mean driving distance is less than his claimed 275 yards. Let's introduce some concepts. The cutoff point, negative 1.645, partitions the range into two parts, one leading to rejection and one not. By rejection region, we mean the set of values for the test statistic that leads to rejection of the null hypothesis. For non-rejection region, we mean the set of values for the test statistic that leads to non-rejection of the null hypothesis. The value or values of the test statistic that separate the rejection and the non-rejection region are called critical value. The critical value is included in the rejection region. In the previous example, the cutoff point, negative 1.645, is a critical value. The rejection region is z less than or equal to negative 1.645, and the non-rejection region is z larger than negative 1.645. Notice that the value negative 1.645 is included in the rejection region. The shape of the rejection region depends on the alternative hypothesis. In the example we just discussed, the alternative hypothesis is left-tailed. Therefore, the rejection region is smaller than or equal to the critical value. For a right-tailed hypothesis, the rejection region is larger than or equal to the critical value. For a two-tailed hypothesis, the rejection region is on both sides, which contains too large or too small values. Suppose that a hypothesis test is to be performed at the significance level alpha. Then, the critical value must be chosen so that if h0 is true, the rejection region has probability alpha. For the left-tailed alternative hypothesis, the cutoff point is thus minus z alpha. Notice that z alpha is the upper tail percentile of the standard normal distribution. For the right-tailed alternative hypothesis, the cutoff point is z alpha. For the two-tailed alternative hypothesis, The rejection region includes areas on both tails. Therefore, alpha over 2 for each part. The critical value is therefore plus minus the alpha over 2. Notice that we have two critical values for two-tailed alternative hypotheses. As a demonstration, let's check the one-mean z-test. For one-mean z-test, the purpose is to test the population mean mu to see whether mu equals a given constant mu0. The example of graph is one-mean z-test problem. In this problem, mu0 is 275 yards. The test statistic is exactly this score, or x bar minus mu0 divided by sigma over square root n. If we set the significance level at 0.05, the critical value can be found according to the different alternative hypotheses. For the left-tailed alternative hypothesis, we have already calculated that the critical value is negative 1.645. For the right-tailed alternative hypothesis, if we want to test alternative mu greater than 275, the critical value will be 1.645. We can see that the probability to the right of 1.645 is 0.05. If the alternative hypothesis is that mu is not equal 275, it is a two-tailed hypothesis. The critical value contains two values, negative 1.96 and 1.96. The probability to the left of negative 1.96 is 0.025, half of the significance level. The probability to the right of 1.96 is 0.025, half of the significance level. Although we have three different scenarios for different alternative hypotheses, there is something in common. Firstly, reject H0 if the test statistic falls in the rejection region. Of course, how to find the rejection region is different for the three scenarios. Secondly, the test statistic is the same. It is always the z-score of your sample mean. This slide summarizes the steps to use the critical value approach to hypothesis testing. First, we need to correctly state the non- and alternative hypothesis. Then, decide on the significance level alpha. The value of alpha is usually a convention. In most disciplines, it is 0.05. Then we need to compute the value of the test statistic. Next, we need to determine the critical values. If the value of the test statistic falls in the rejection region, reject H0. Otherwise, do not reject H0. Last, interpret the result of the hypothesis test. For different hypothesis testing problems, it is possible that we use a different test statistic or find critical values using a different approach. However, the above general steps always follow. We will discuss more concrete examples on one-mean z-test in later sections.